Welcome back to Engineering Mechanics, EGM 3512. And after we talked about truss structures last lecture from a method of joint standpoint, we are now talking about the method of sections, and I will define that term for you today. But before we talk about that particular procedure, let's talk about our actual goal and objectives today. So what we will do now is introduce rotational equilibrium for our analysis. Remember that for the method of joints, we only used the sum of the forces in X and the sum of the forces in Y. And now we are adding rotational equilibrium, meaning the sum of the moments about a point. And that will help us to calculate our forces in a truss system, the member forces. So I will introduce to you how that is done. And then I will also continue with another thing that we talked about last class, which is the zero force members. So those zero force members are quite often available in larger truss structures. And for larger truss structures, we use the method of joints. So it makes sense to talk about those in the context of trusses in this lecture. And then our ultimate goal is to use the method of sections just to determine a maximum of 3 member forces. And you probably already can guess where the 3 comes from. So the third condition comes from the fact that now we're adding the rotational equilibrium. And so I have the 3 conditions: sum of the forces in X, sum of the forces of Y, and sum of the moments in about any point. So that we can use to calculate 3 member forces in any truss structure. Let's get started and let's actually talk about the rotational equilibrium, as this is necessary to properly use the method of sections. And to do so, I will first draw a random truss structure for you, similar to the one that we talked about when we talked about the method of method of joints. So I'm going to use a very same type of structure here. And then we will analyze it using the method of joints. And of course, this is just the conceptual approach here. And in later slides, we will actually use the methods to find our numerical answers to problems like that. So here I have a system that is simply supported, and I should just give it nodes A, B, C, D, and E. And also for good measures, remember that these are all hinges technically, although we usually don't show them at the end anymore. And a very common question now would be, hey, please find the internal forces in, let's say, ED, BD, and BC. And if you remember how we did it with the method of joints, so if we would use the method of joints and we would find our external support reactions first, then we could, for example, start to calculate these member forces here at this node and then bring our forces up here and move our way into the structure and around. And as we already talked about last class, the method of sections is a little bit complicated when you have larger and larger structures, because you have to work your way in from the outside. And with the method of sections that we're talking about here now, I can in one scoop really release 3 internal forces, because now I have the rotational equilibrium. But I want to explain that to you now in more detail. So I can now pretty much release the entire system on one side. So for example, on the left side, and have this cut, I'm going to call this cut 1. But I also could have done it exactly on the other side, which is cut 2, and to no surprise, both of them have to give the same results. But to clarify that a little bit more, I will now draw the very same structure separated at that cut, and that looks like this. So I have the left side cut here and the right side cut of the structure right here. And by doing that, I effectively separated and released the internal forces at those locations. So I will now introduce my internal forces, which are only normal forces, just like we talked about before. So I have a normal force in line with each member. And those are usually similar to the method of joints. They are assumed to be in tension first. So I'm going to do that right now. So I'm going to assume this here. This would be DE to be in tension. BD would be also assumed to be in tension. And BC would also assume to be in tension. And if that's the case, then I have to do it on the other side the same way. Of course, this is also DE. I have BE here, and I have BC here. And so now we probably already understand that we can separate these structures and we can cut, because remember that in mechanics the cut always works as long as you bring the forces back in that you released. And now we have to find out how can we generate equilibrium for each of these cuts, because remember, equilibrium must pretty much exist for this system here just as it has to exist for the other side system. But to do that now, we can try our regular trick, right? So we can try our sum of the forces in X is equal to 0. And if I were to do that now here for the left cut, let's say, then I had plus DE minus BC, or also plus BC in this case. And so I have two unknowns. But let's just write that down for now. But before I do that, let me introduce the support reactions as well. So RAY, and here we of course have RCY and RCX. How to calculate those is not part of this lecture, but now I have all my external and internal forces, and I'm just gonna now go back to this equation here. So the sum of the forces in X is equal to 0, and 0 would be equal to plus DE plus BC, but also plus BEX, right? So we have first DE, BC, and also the X component of BE. So we have one equation with three unknowns effectively. So that does not really help us as of right now. Let's try the sum of the forces in the y direction being equal to 0, and 0 is equal to, and again, I'm looking at this left cut here. Of course, it's true for the right side as well, but I'm looking at the left side. So 0 is equal to plus RAY, which usually would include a value. And then the only other thing that has a vertical component actually is BE. So we would say plus BEY. Right? So let me clarify that real quick. So BE has, of course, a horizontal component and a vertical component. And in this case, since we assume intention, they go to the right and up first. And so now you can tell already from this picture that BE would have to point down against RAY. But even if I can solve this equation now, so this is solvable, right? So this equation is solvable. So let's make that note here. So this is solvable. But even if I find BEY, then what I would end up with is solving BCX, and I still have my two unknowns here. So therefore, I reached an end pass, and I need to find another solution. And of course, from the introduction of the lecture, you already remember that now I'm using the moment rotational equilibrium to solve this problem. And this is where the trick in the method of section lies. Remember that when we find the sum of the moments about a point, we usually when we find, for example, let's say RAY, then we usually take the sum of the moments about C. And the reason we're doing that is not because it wouldn't work at any other point. In fact, the sum of the moments about any point needs to be zero in an equilibrium system. But the reason we're taking the sum of the moments about C is because RCY and RCX disappears and we only have one unknown, which is RAY, when we rotate about this point. So this is a condition that's always true, right? So if you find any point in any structure where all but one unknown disappears, then you can easily set up one equation with one unknowns. And so if now I start to use the sum of the moments here as my third equation, sum of the moments being equal to 0, I need to find a very interesting point to rotate about. And so the question is, which of these ones here, or where would be a point for this cut to take the sum of the moments about, so that like I only end up with one unknowns. And if we look at that, we have 1, 2, 3 unknowns, but 2 of them meet in one point. And in fact, you can tell that from the way I named them. So there's BE and BC. They share one letter, the B, and therefore they get together at this point. And that means if I take the sum of the moments about this point, then the only unknown is DE. So let's write that down, how that works. So I would take the sum of the moments about B, and let me just also include some dimensions here, or some random dimensions, if you will. So I probably need this dimension from here to here. I'm going to call that A. And then I will also need the vertical dimension, which would be along this line. So that would be here and here, and I'm going to call that B. All right. So now what I end up with is 0 is equal to, and I'll say that again, we're taking the sum of the moments about point B, so about this point here. And so I have RAY that has a lever arm about this point. I have DE that has a lever arm about this point, but BE and BC do not. So therefore, I'm going to start with my unknown usually, which is DE in this case, DE. And that is multiplied by B. And I need to, of course, obey to my rotational sense. So this here turns clockwise about point B. So therefore, it's negative. So negative DE times B. And the only thing that opposes this in this particular cut is RAY times A, right? Because it has the distance of this chord here on the bottom. And I just named that A. So if I write that down, that would be RAY multiplied by A. And in this case, RAY rotates counterclockwise about B, so therefore it happens to be positive. And because there's only effectively one unknown now in the system, right? So the only unknown is DE, and therefore I can solve this. So I can solve this for you right now, but that's not really the point of the concept here. So DE would be equal to RAY times A divided by B. And that I can solve now. And now you can see that I have also solved now for DE. And so I can use that DE in this equation up here. And then last but not least, I could solve for BC, which is my last unknown in this equation now. So I can solve this. So that technically concludes the method of sections. But let's make sure that we really get the concept, and let's actually look on the left side and cut 2 here. So in cut 2, this works as well. And if I wanted to find DE as well, then all I would have to do is find the point where the other ones disappear. And it is still true that it's at node B, except that node B now is outside of this cut. And that is often confusing to students, right? But there's no difference because the sum of the moments about this point, 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 any point is equal to 0. So you cannot get confused, or you should not get confused by the fact that the point about which you rotate the system is actually outside of your cut cloud, as I call it, right? So I call this here my cut cloud number 2, and it's outside that rotational point. But for clarity, I'm gonna draw the structure just with like dashed lines here. That's often how you see it in books. So I will use my ruler here, and I will pretty much designate this here as point B. This is the point B, or node B, which is outside of my cut. But let's set up the equation for that one. And I'm going to do that up here. And so I now need my dimensions again. So because it's a symmetric system, at least in my head it was a symmetric system, but I'm going to also call this here direction A, and the height is still B. Or I should have called it H, but it doesn't really matter. So this is B. And it's the same as it is on the right side. So just to be clear, here on the right side, I have these 2 dimensions. So the entire system is pretty much 2A long. So from here to here, we have A and A. And then the height is B. So now you know for sure what's going on here in the system. But let's set up the sum of the moments about that point here. So the sum of the moments about this point, which is again outside of the cloud. So to find DE, I will say the sum of the moments about point B is equal to 0, counterclockwise positive, and 0 is equal to, I start with my unknown, DE multiplied by B, and that is turning counterclockwise, therefore it's positive. And now I also have to consider RCX and RCY. RCX actually points right through this, the line of action of RCY is going right through that point. So that goes to 0 once again, but RCX has a value. And so RCY multiplied by A. And that rotates counterclockwise, therefore it's also positive. Right? And I can solve this now for DE. So DE again is RCY multiplied by A divided by B. And to be fair, like, we have not included any force on the top here, or like any external force except the support reactions, but you would just include them. So I'm going to do that now just for your study notes here. So let's say I have a force F1 here. Then that would be only in the cut number 2. So you would find that here as well, F1. And of course, that would have an effect on your support reactions, and we didn't calculate those right now. But it would be reflected in RAY and RCY. And so in the equation that we wrote down here, it would have no effect, right? Because for this equation that we wrote down here, we only worried about this cut on the top left. Whereas for this cut here, we include F1. So I would have to add this here to my equation, and I'm going to do that for you just for good measures and to have all the possibilities covered here. So let's see where we would add that. So we would have F1, and that would now be technically multiplied by A over 2, right? Because we assume that node D is exactly halfway between node B and C. That's not very precisely drawn here, but that's usually how those structures are geometrically arranged. So F would be right at this point, returning about this point, so A halves. And in fact, it's turning it's turning clockwise, so therefore it's a negative part. And so I also need to include that. in my equation here. And so if I substitute that, then we would have RCy times A minus F1 times A, and all of that divided by B. Sorry, this is A over 2, right? And all of that divided by B. So that's how dE would look like if we had the force in there. But I think the general concept here gets clear, and that is that you can cut the system anywhere you want, except you have to worry about no more than 3 members, right? So we can only cut through 3 members and not more, because we have only 3 equilibrium conditions. But as long as you cut through any 3 members, preferably through 3 such that 2 meet in one point, then you can always apply this method. And that is the method of sections conceptually. We will, after we talk about the zero force members, we will actually use this in action and calculate some numerical values. But first, let's talk about zero force members. We already started talking about zero force members just analytically in one of our last examples when we talked about the method of joints. And what you've seen there was actually a joint that looked something like this. So there was a hinge here. We cut through one member, another member, and another member. And I already told you that we had 2 parallel members. So 2 parallel members that were jointed by, and I purposely said that last time, by a random third one. This one here actually happens to be not random. It's actually perpendicular. But remember that for this case here, it's easier to see that any force that is acting perpendicular to this system cannot be resisted at this node, because you cannot create equilibrium here. So let's say you pull on this member, it's not resisted up here. So therefore you only have one force in one direction, and therefore you cannot create equilibrium. That means that this member here must be equal to 0. And therefore this actually works for any scenario, not just for the perpendicular case, but I can have the very same scenario. So let me redraw the system here, and let me join a third one, which now is actually under an angle. And often students think, now it's under an angle, now that it cannot be a zero force member anymore. But remember, we cut through the system here and here and here, and the red component here, or the one that is not parallel with the other 2 ones, actually has a vertical component and has a horizontal component, something we dealt with very early in this class. And so this vertical component here, it may go up, it may go down, it doesn't really matter, but because it cannot be balanced at this point. So there's nothing here on the top that can balance this or can counteract this. And therefore, this must be a zero force member. It doesn't matter what the angle is, it has to be a zero force member. The 90-degree angle is just a very special case, and you see that often in real life because it's easier to fabricate it that way and so on, and there's other reasons for that too. However, analytically, you will always find that this must be 0 because there's nothing to balance this. So, and I'm going to call this case 1 here. So case 1. And the way I would write that down under case 1 here is I have 2 parallel members that are joined by a random third member. If that happens, the random third member must be 0. But not to worry, even if you don't see this in advance, you often get there analytically. Like it comes out when you write your sum of the forces at x and sum of the forces in the y direction. at any node, this will always resolve itself. So if there's a case 1, you can already tell there will be a case 2. So let's write down the case 2 here on the other side. And what is the case 2? And that is when you have an external node. So that looks like this. And that is not loaded. So now I cut this one. So I have 2 external members. And the structure can continue here. Like there's whatever something is going on there. It doesn't really matter. I can maybe draw it like this. And it doesn't really matter what goes on there. The matter of the fact is that this is an external node that has no load on it. And so for now, I pretend there's a load on it. And if you have the load there, then you would probably see that the vertical component that is acting in this member could balance that. But remember, in this case, the second case only talks about the fact that it's an unloaded external node. So if that force is not here, there's no force here, then this one cannot balance it. And also this doesn't matter if this is horizontal or vertical, it's an unloaded external node has only 2 members acting on it. And if that's the case, you cannot have any load there. So let's draw another scenario here. So for example, let's say I have a node that looks like this. And who knows what else goes on in the structure. So maybe I have something that goes on like that. And whatever else happens there, we don't care about. All we care about is that I have an external node that is not loaded, right? And so that is our case number 2. So let's write that down. So case number 2 is 2 external members come together at an external node, which of course is necessary, otherwise it wouldn't be an external member, but this external node that is unloaded or that is not loaded. So it doesn't carry any load. So those are my 2 cases, right? I have first the case number 1, which was discussed up here. Let's look at that again. So the case number 1 is 2 parallel members that are joined by a random third one. And case number 2 is any external 2 members that come together at one joint. And please note the word 2 here. So in fact, let's maybe highlight it. So here the word 2 is important, and external node, and not loaded. And since we're highlighting, let's also talk about the parallel members here that are joined by a random third one. So then the random third one must be 0. And you can use this now to pretty much analyze systems before you actually run any numbers. And this can become helpful, as you will see on the next page. So let's look at these systems here. And it's a very straightforward exercise. All we're asking you is to find all zero force members before you even start your calculations. You can use these to practice calculating the method of sections or method of joints, but that is not the point here. Right now, we're trying to look at each of these systems and try to identify the zero force members. So these systems all have zero force members, and let's try to identify them. So I start here on the top left, and what I see here in node E is 2 parallel ones with a random third one joined. It actually is not random, it's 90 degrees, but the rule is random. And I have the very same effect here at node B. 2 parallel ones and the random third one. So what I can do, and the way I show this, is I cross these out. This is how you would show it on an exam, but for the next ones, I just erase them so that you can see what is actually part of the structure. So let's look at this one here on the bottom. So Here I have this case very often, and this will become very interesting because for the first time now you will see that this actually carries through. So here at node E, I have two parallel forces, and there is a random third one that joins it. So now let me try to zoom in to do a better job here of showing this. So effectively member EC does not exist. So I can literally erase this, and that is how that would look like. And so now you see what's happening. It's actually such that now member CF is having the same condition. So now I have this structure here, these two parallel structural members are joined by a third one, and therefore I can erase that one as well. And so what I end up with is a structure that looks like this. And once again, now I have this condition at node F. I have two parallel members which are joined by a third one, and I can also erase that. And one more time, I can do the same thing at node B, and I don't think I have to explain that anymore. It's the same concept. And now I'm effectively done. So believe it or not, this entire structure actually is just reduced to these three members that you see. So effectively we have a member AD, we have a member DG, and a member AG. And that's all this structure needs. All the stuff in between would not participate in carrying the load. And you can always show that numerically as well. Let's move on to the next structure. Let's take the one here on the bottom. So now what do we have? We have here we have two parallel forces and a random third one, but be careful now, there actually is a load now. So this cannot go to zero, right? If this would go to zero, this node would just not be able to resist the 2 kilonewton that's acting on the structure. So here, be careful. So that is not a zero force member. However, here at node F, it is a zero force member for the reason that we have two parallel forces and a third one here that goes in that direction. So once again, I can just erase this, and there we go. And once I've done that, you already see that I have the same condition now at member D, or like I guess at node D, and member DG has to disappear. And so I'll do that real quick. So that now is gone as well. And do I have any other zero force members in here? I don't think so, right? So let's continue to look at it. Yeah, here I have parallel members with a third one joined, but I also have this force acting here. And so therefore that's not zero. Same is true here. And since that is true here, this one also cannot go to zero. So I'm done with that one. Let's look at the next structure. So this one here on the top, what do we have going on here? I would say we definitely have a zero force member here because parallel and an unloaded third one. So let me make that disappear. So that's gone now. Do I have another one? Yes, I do. And that's a little bit deceiving again. I actually have two more ones because here I have actually the second case that we discussed, and that is the external unloaded node here. So there's an external node unloaded, therefore this has to disappear as well. So that was the second case. So the way that looks like is like that. This would have not participated in any load carrying activities. And that is not the case at node J, as you see here. Why is that? Because there is actually a load acting on the system. But so now I'm done with this and I can move on to the next one. And that one looks a little bit scary initially, but maybe we can also reduce this. So which ones participate in a load carrying and which ones don't. Here again, I have my parallel ones and the random third one. So let me erase that one. So that goes to zero. And I think that's it for this structure. Yes, this is it. Everything else. So don't get me wrong, there might be another zero force member, but none one that jumps into your eye and that you can immediately see. So last but not least, here we have the node D, and node D again has this condition where this has to go to 0. And now node B has the same condition, so that has to go to 0. And therefore, the real structure that participates in the load carrying mechanism does look like this. And that concludes our zero force members. Let's take a look again. So on an exam or somewhere on paper, I probably would use this method to identify what is my zero force members. But here I was lucky enough to just erase it and to clearly show how the final structure looks like. But you should use this method to cross out the members and to really understand where those forces are zero. And with that said, we are done with the zero force members, and we can now go into our method of sections and run some numbers. So let's look at this problem, and as always, we always read our problem first. So what is asked of us here is use the method of sections, that's very important, to calculate BC, FG, and CG. So first thing I should do is identify where those are located. So BC would be right here, then FG would be right here, and last but not least, CG would be right here. And I have two choices now. I can just cut the left side, which is probably what I will choose to do, because look at it, it's a cantilever and I don't have to worry about support reactions that way. Or if I want to make my life complicated, I can also use the second cut here, but then I would have to calculate all my support reactions first. So I think that would be a waste of time for us. So first thing I do is I draw my free body diagram for my cut 1. So let's do that. So cut 1 and draw the cut so that I can use it as a free body diagram for my identification of the relevant points and such. So I have this system here, and I also have this force. And let us bring down our forces. 1000 Newton. That's 1 kilonewton actually. And again, remember that we cut the system. And let's identify our forces. And originally, we always assume everything to be in tension. And we are dealing here with BC up there, CG, and GF. And now I can look at my system here first and identify what unknown I want to start with. So let's evaluate it. The sum of the forces in X is not a good idea because I have 3 unknowns acting in the X direction. That would give me 3 unknowns in one equation. That is not good. The sum of the forces in Y would actually work very well because I have only two forces that act in the Y direction. So that is the part here in CG and the 1000. So I can do that without any lever arm. So maybe that's the one I start with. So let's say I want to find CG by the sum of the forces in the Y direction being equal to 0, upwards positive, and 0 is equal to plus CGY minus 1000 Newton. So I know that CGY is equal to plus 1 kilonewton, and the plus tells me that I assumed correct, so therefore it's actually going in the upwards direction, which means it's in tension. So I got that figured out, and now I need to, of course, convert from CGY to CG, and I have to do that using dimensions, but I guess we're lucky in this case because it seems to be a 45-degree triangle. So therefore CGY is equal to CG x is equal to 1 kilonewton, and the CG itself is equal to the square root of 2 times 1 kilonewton. And that is equal to 1.414 kilonewton. So I already calculated that. In fact, that is something that we were asked for, so I can already double underline that. And now I can calculate my other forces. So let's see which one we want to do next. Sum of the forces in x doesn't work. We already talked about this. So I need to use the sum of the moments. And let's look at which point we want to take the sum about. So I have two options here. I can either find GF or BC first. If I want to find BC, I would have to take the sum of the moments about which point? Exactly about point G here, because the line of action of this force and the line of action of this force pass through that point, and therefore it disappears. However, similarly, if I want to find GF, I could also take the sum of the moments about point C, right? So let's look at that. So point C is right up here, which would be outside of the cut, but it would be here. But BC and CG have a shared letter, the C, and therefore it disappears, right? So I'm going to repeat that again. I said it when I introduced the method of sections. If there's a shared letter, usually they meet in that point. So BC and CG meet, but also CG and GF meet. And so again, if I want to find BC, I take this point with the shared letter G, and I take the sum of the moments about that point. But if I want to find GF, then I need to take the sum of the moments about C, which is BC shared with CG letter, right? So they both share that letter C. So I just have to decide now. Let's see which one I'm going to go with. So I guess because it's an educational problem, I'm going to pick the one that's up here, right? So the one where those two come together, because that is outside of the cut, which often is problematic for students, and it's always good to practice the things that are problematic. So let's do that. So let's take the sum of the moments about point C. Sum of the moments about point C is equal to 0, counterclockwise positive, and 0 is equal to, I start with my unknown, GF multiplied by 2 meters, right? So the height of the structure is 2 meters. 2 meter. And now I have to decide what the rotational sense is. So if I assume GF in tension initially, it turns counterclockwise, so therefore it's positive. So positive GF. And then I also have the 1000. Well, so I'm going to make that a kilonewton in this case. So kilonewton, 1 kilonewton. And that is multiplied by, be careful now, 4 meters, right? So 2 times 2 meters. So let's write it down this way, 2 times 2 meters. And my rotational sense is turning about that point this way around. So that is counterclockwise. So therefore it's also positive. So that's positive. And now I can solve this for GF. So GF actually happens to be negative 1 kilonewton, so that's 4 kilonewton divided by 2. Right, so that is effectively 2 kilonewton. And the negative tells me that it's actually in compression, since I assumed tension originally. So GF technically, if I go back in here, so let me take a faint green pen and say that GF is actually going in with 2 kilonewton here. And now I could use the sum of the forces in the y direction, sorry, in the x direction, to put this in equilibrium with this and this. And let's actually give that a try. So again, it's an educational problem. So now I can use the sum of the forces in the x direction being equal to 0, positive to the right, and 0 is equal to minus 2 kilonewton plus the horizontal component of Cg, and we calculated that before. So Cgx is 1 kilonewton, right? So we have that given here. So 1 kilonewton, and that was actually in tension, so we were correct there. So it's plus to the right, 1 kilonewton, and then plus BC. And you can also call that BCX. And that is assuming that it's in tension. And so therefore, BC is equal to 1 kilonewton in tension. So I assume correct, right? Because the answer is plus here. And that, by the way, is also a result. So I'm double underlining that. Similar to my 2 here, that was also a result. And now I solved the problem. So let me go in here with green and let's agree that this was 1.41, 1.414, and BC here was equal to 1 kilonewton. So now we can look at the entire system or the entire problem again, and we solved for our 3 member forces here by using the cut 1. We could have used the cut on the other side, and I encourage you to do that because you probably want to be able to calculate support reactions for your upcoming exam, and you also want to be able to practice the method of section here. And by the way, you can also use the method of joints to work your way in here and to validate your results. So you will easily have a tool to find out if you are right or wrong, pretty much to check your own work. And I encourage you to do that for problems that are as small as these ones. So you just find the internal forces or the member forces by using the method of joints and the method of sections. And that will help you to gain confidence and solve more of these problems. Let's solve another problem. Let's look at this method of sections problem. So what are we asked here? Let's look. So method of sections and AB, BF, and EF. Let me identify those. So AB would be right here. BF would be right here. And now there's a trick. There's EF here. And you would think, hey, if I cut through all these members at the same time, I cannot use my method of sections because I'm cutting through effectively 4 members, right? 1, 2, 3, 4. But note that EB is a zero force member. And if you don't see that, then that can be problematic in an exam because you would probably trip over your understanding of that. And that could make your life difficult. But here, EF doesn't exist, so I'm erasing it for you. And now the problem is effectively like before, but for good measures, we can now go through that exercise, or actually I'm leaving that up to you, and I will solve the next problem for you or with you. So let's look at the next problem. And here we're gonna calculate the members CD, CH, and HI. So I have to identify those. CD would be right here. So CD is right there. CH would be right here. And HI would be right there. So I have 2 options now. I can either make this cut here on the left, or I could do the same thing here on the right. I'm not sure which one is easier yet. I have to evaluate that. I would say that I'm going to take the cut number 1 here and not number 2, simply because I only have one support reaction to deal with. So I'm going to have to calculate that support reaction RFY first, because that's the roller. So let me do that. Let's calculate RFY first. RFY is done by the sum of the moments about point A being equal to 0, counterclockwise positive, and 0 would be equal to RFY multiplied by, let's look at it. So the distance from here to here horizontally is 4 meters, so multiplied by 4 meters. And then I also have to include all the other external forces, right? But before I do that, I need to set a rotational sense. RFY is turning clockwise, so that's negative. And now all my other forces, so 40 kilonewton. Multiplied by 2 meters. And that rotates counterclockwise, therefore it's positive. The 50 passes through the point of interest, so I completely ignore that, but I can worry about the 30 and the 30 here, so I have to include that. So 30 kilonewton, and that's the same one multiplied by 1.5 and by 3, right? So I have 1.5 plus 3, and that's in meters. And they both rotate the same way around, otherwise I couldn't have combined those, but they both turn counterclockwise, therefore that's also positive. And if you solve that, you will find that RFY is equal to 57.5 kilonewton, and that is positive, therefore we assumed correct. So here we have 57.5 kilonewton. So now I can easily cut or work through my cut number 1. So let me just use that for interest of time. I'm just going to introduce my forces here in that direction, in that direction, and in that direction. So I can now use my cut 1. And in fact, what I will do, just to make my life easy here, I'm going to erase the other part of the structure so we can easier see what's going on. So all this is gone. And now I can use my sketch here. So to do that, let me bring down that force, and this force. And the easiest one to calculate is probably HI, right? So this here would be HI. This would be HC, and we have CD up there. And the easier one to calculate would probably be H1 by taking the sum of the moments about point C, because then CD and HC disappear and all I have to deal with is HI. So let's write down that equation. So I'm interested in calculating HI, and I do that by the sum of the moments about C being equal to 0, counterclockwise positive, and 0 is equal to HI multiplied by 2 meters. What is that lever arm? Let me show that to you. So that's the lever arm from here to here, which is 2 meters up here. And it's actually rotating counterclockwise, so therefore that is positive. Now I have to include all the other ones. So let's start with the 50 kilonewton, which also has a lever arm of 2 meters. So 2 meters is turning also positive. Then I have the 40 kilonewton, which has to be multiplied by 4 meters. And that is also turning counterclockwise, so therefore positive. And last but not least, I have RFY. So RFY, but keep in mind we already solved this to be 57.5 kilonewton multiplied by 6 meters, right? 6 meters. And that is turning clockwise, therefore it's negative. And I can now solve this for HI by just rearranging the equation, and HI would be 42.5 kilonewton positive, which means it's in tension, or we assumed correctly. So yes, this here would be equal to 42.5, or I just double underline my result here. So now I solved that one. How do I find the other ones? For example, the next easier step probably would be to calculate CD, right? So let's look at CD, and I can do that by the sum of the forces in the y direction, because CD is the only one with a vertical component that is unknown, that is left. So upwards positive is equal to 0, and 0 is equal to minus CDY, vertical component, minus 42.5 kilonewton, minus 50, because it's going down, kilonewton, minus 40 kilonewton, plus 57.5 kilonewton. And so now I can rearrange that to find my CDY, which is equal to negative 75 kilonewton. And that means that it's actually in compression. So, and that is only the vertical component, the y component. So let's look at this again. So I have 75 going up here. So that's 75. And if you remember correctly, we actually had a distance of 1.5 meters. I erased that here earlier when I made my sketch, but I have a distance here of 1.5 meters. And so my actual length of CD, so LCD, is actually equal to 2 squared plus 1.5 square root squared, and then square rooted the whole thing, which I believe is equal to 2.5. So I have a length of 2.5, so I can use that now to use my relationship, my triangular relationship, right? So I can say that 75, I have to write this down here, so 75 kilonewton corresponds to 1.5 meters, just as CD in kilonewton corresponds to 2.5 meters. And therefore CD is actually equal to 75 kilonewton divided by 1.5 multiplied by 2.5. And that then is equal to 125. So 125 in compression. And that is a result again. So CD here now is equal to 125. And so I almost done. All I need now is my HC, and HC is only acting horizontally, but don't be fooled, there's also a horizontal component here. So I have to include that. So my horizontal component here technically is going in this direction, and let me fix the CD here as well. So remember that CD here is actually acting upwards. So that's going in this direction because it's in compression, but we already wrote that down below. But I now want to calculate CD horizontal. I'm going to do that down here. So CDX is equal to 75 kilonewton divided by 1.5 multiplied by 2. That's the same similar triangle that I had before. And so CDX is actually equal to 100 kilonewton. So now I know what that is equal to. And if I look at the entire cut here, I know that this component here is equal to 100. And so the only two things that act in the horizontal direction is this 100 and this 100. Everywhere else I have nothing that is horizontal, so I know that HC is actually 100 to the right, and that would be in tension. So I'm not even bothering writing that down in an equation form, but this is 100 kilonewton in tension. And now I solved all my three forces, and I believe you have all the tools you need now to solve problems with the method of sections or with the method of sections approach. So let's recap this problem real quick. We started with calculating the support reaction for only one support because we only needed one side of the system. Then we found first the HI component because it was the vertical one that could be calculated by taking the sum of the moments about node C here, and that's reflected in this equation, which gave us 42. And since I now had only one unknown in the y direction left in CD, I was able to use the sum of the forces in the y direction to solve for the 75 in compression. And then I used that to calculate my horizontal component in CD, and that I could use to find HC. So it's a logical way through. And so the problem usually for students is not to solve these types of equations. The numbers are very easy, and often they can also set them up. The problem is really to know where to start and how to start. And I say it again, it's very important to understand where to take the sum of the moments about to get started with these types of problems. But I believe you have now enough resources to study this material, and I wish you good luck solving that. However, let's take a look at the conclusion of the lecture. So, of course, you can write down what you learned and what takeaways were. You also should write down what is not clear and what needs clarification for a better understanding. But this part we're going to go through together just to check it off. I definitely know how to look at truss structures and how to section those off now. That is something I clearly understand. I also know how to apply what's called the rotational equilibrium. And of course, you have done this many times before in this class, the sum of the moments being equal to 0 to find the member forces. And the trick here was clearly to remember that I need to find the common point where two forces of the three that I identified disappear. We also learned in this section that I can identify the zero force members and how to distinguish those two cases. And I need to, of course, understand that often when I eliminate those zero force members, my calculation effort becomes much less, or it reduces significantly. And then next, I am also able to calculate those three random forces by using the method of sections, which really stands for sum of the forces in X, sum of the forces in Y, and sum of the moments. So I use all those interchangeably. And then last but not least, I of course need to understand if they are in compression or in tension. And I think we covered that in detail. And when in doubt, always start with assuming it to be in tension. And then if you get a positive result, you were correct and it was in tension. If you get a negative result, then you should invert your logic and assume that is a compression member. So that takes us to the homework now. Let's take a quick look. These problems are very similar to the ones you've done before, but notice here that for the very first three problems, you are actually forced to use the method of sections, or I don't want to say encouraged, you have to use the method of sections. But for these following problems, you can use any method you want, like either the method of sections or the method of joints, whichever you find more reliable for you to use or you find quicker. And you can do that as you are pleased. However, I would recommend that you use both methods to kind of check your work, and you should do that anyways in practice and preparation for your exam. And then there's some strange looking ones here at the very end. Don't be confused. Some of these structures have a lot of zero force members, and some of these are very impractical for real world use, but they get the educational point across, and the goal here is really to understand the method of sections and not to have a system you can really use. I mean, don't get me wrong, most structures in this class are really usable, but here this is really for you to comprehend the method of sections and the method of joints. And therefore we build in some tricks that you sometimes may not see in the real world, but it will help you to comprehend how the real world actually works. With that said, good luck in your homework, and I will see you in the next lecture.